Hey, before we look at our next technique of integration, it will be useful for us to review a little bit of right triangle trigonometry. Okay, so start with a right triangle. Designate one of the two non-right angles as the angle theta. And we can refer to the sides of the triangle as the side opposite the angle theta, the side adjacent to the angle theta, and the hypotenuse, which is the side opposite the right angle. And we can define the elementary trigonometric functions in terms of ratios of these sides. For example, the sine of theta is the opposite divided by the hypotenuse, cosine of theta is the adjacent over the hypotenuse, and the tangent of theta is the opposite over the adjacent. And the other three elementary trig functions work similarly. For example, the secant of theta, which is 1 over the cosine, is just the hypotenuse over the adjacent. We also have the fact that since this is a right triangle, the Pythagorean theorem holds a squared plus b squared equals c squared, or adjacent squared plus opposite squared equals hypotenuse squared. And this lets us work out some interesting problems. And what do I mean by interesting problems? I mean problems like this. Suppose you know the sine of theta is 1/4. How do we find the tangent of theta? And what makes it interesting is really that in our next integration technique, after we do a bunch of work, we're going to come up with problems just like this, where it comes down to just a little bit of trigonometry in order to get the answer. We start by drawing ourselves a right triangle, labeling one of the angles theta. And then there are a number of ways we can assign lengths to the sides of this triangle so that the sine of theta is equal to 1/4. But the simplest is probably just to make the opposite equal to 1 and the hypotenuse equal to 4. Certainly we could have made the opposite equal to 100 and the hypotenuse equal to 400. That also would have given a sine of 1/4. It just would have made the arithmetic a little bit more complicated. So we'll do the simplest thing and make the opposite side 1 and the hypotenuse 4 so that the sine of theta is 1/4. And if we knew the length of this last side, which I'm calling A here, then we'd be in great shape to find the tangent of theta because the tangent is just the opposite over the adjacent and A is the adjacent. Well, how do you figure out the length of the side A? You use the Pythagorean theorem. The Pythagorean theorem tells us that a squared plus 1 squared is equal to 4 squared, which gives us that a squared is equal to 15, since 4 squared is 16 and we're subtracting 1 squared, which is 1. If we're careful with the algebra, that tells us that a is either positive or negative square root of 15, but a is a length, so it certainly can't be negative, and that tells us that a is the square root of 15. And now we're in great shape to find the tangent of theta. The tangent of theta is the opposite over the adjacent, which is 1 over the square root of 15. We don't usually leave it that way. It's good practice to rationalize the denominator. And we get that the tangent of theta is the square root of 15 over 15. Okay, same example, same triangle, same picture where the sine of theta is 1/4. Instead of looking for the tangent of theta, what if we need to figure out what theta itself is? So how do you look at that triangle and determine what theta is? Well, theta is defined as being the angle that has the sine 1/4. That makes theta, by definition, the arc sine of 1/4, or the sine inverse of 1/4. The angle whose sine is 1/4. We've got a great name for it. It's called the angle whose sine is 1/4, or arc sine of 1/4. So if you ever need to know theta, which we will sometimes in a situation like this, that's how you do it. If you know that the sine of it is 1/4, then the angle theta is arc sine of 1/4. In case you don't like that reasoning, start with the equation sine of theta is equal to 1/4, and then just take the arc sine of both sides, and use the idea that arc sine is the inverse sine function to get that the arc sine of the sine of theta is just theta. And so once again, theta is the arc sine of 1/4. Okay, let's do one more. You try this one. This one is actually going to come up in a problem that we work on soon. So you've got that the sine of theta is x over 2. See if you can find the cotangent of theta. Start by drawing a right triangle. Take a few moments, pause the video, see if you can work your way through it. When you're ready, start it up again and we'll do it together. Okay, you draw your right triangle, you label one of the angles theta. The sine of theta is x over 2, and the easiest way to make that happen is to make the opposite side equal to x and the hypotenuse equal to 2. We will once again name the remaining side a, and then use the Pythagorean theorem to compute a. The Pythagorean theorem tells us that a squared plus x squared is equal to 2 squared. And you do a little algebra and get that a is the positive or negative square root of 4 minus x squared. And as before, we throw away the negative answer because it's a length that we're talking about. And so the unknown side there, has length square root of 4 minus x squared. We're trying to find the cotangent of theta. The tangent of theta is opposite over adjacent, so the cotangent of theta is adjacent over opposite. And so the cotangent of theta is the square root of 4 minus x squared all over x. And that's done. The only place you can get yourself into trouble is if you think that there's some kind of simplifying that you can do there. There is not. That does not simplify any further. And just as a quick algebraic trick that you can use in all kinds of situations, if you weren't sure and you thought maybe you could simplify that, well, simplify it how you think you can. But then plug in some numbers for x and see if you get the same value when you plug them into your new expression as you do when you plug them into square root of 4 minus x squared over x. You should get the same value for all possible values of x except possibly x equals 0, since in this expression, this expression is not defined at x equals 0. But if you plugged in 1, for example, you should get square root of 3 over 1 or square root of 3. So if you simplify that, in quotes in some way, and you plug in x equals 1, do you get square root of 3? If not, then you made a mistake. Okay, that was our brief review of right triangle trigonometry, which we will find very helpful when we start looking at integration by trigonometric substitution, which is the next topic. See you soon.